welcome to the Deep Dive. Today, we're pushing beyond AI that just finds answers. We're talking about AI that actually does the research. We're getting into the world of AI agency, these systems that can tackle really complex, long investigations autonomously, stuff that might take a person hours, maybe even days. Our focus, a big name in the open source space, Tongyi Deep Research. It's a model and framework from the team at Alibaba, and our mission for this deep dive is pretty clear. We want to unpack the novel techniques they used. How did they build this state-of-the-art AI researcher?
And what's really grabbed people's attention right away is this balance they've struck, power and efficiency. So Tongyi Deep Research, it's built on a model with 30.5 billion parameters total, which is, significant.
8 billion. Okay.
But here's the kicker, and this is the key thing for you, the listener. It only actually activates 3.3 billion parameters for each token it processes.
Wow, okay. So big potential power, but very lean in operation.
Exactly. And that's not just like a minor detail. It points to this really important trend, building powerful AI agents that are also efficient enough to actually deploy and use widely.
That efficiency angle definitely hooks me. How do you achieve that? How do you keep that research capability, that depth, while staying so lean?
Okay, let's unpack this. I mean, the fundamental challenge with any deep research, any multi-step thing, is always memory and planning, right? How did they design this agent to handle just the sheer volume of information you need for research without, collapsing, getting lost?
Well, they started with something familiar, the REACT framework. That's pretty standard now. Synergizing reasoning, the thought part, and action.
Right, thought, action, reflection.
But REACT by itself, it kind of struggles when tasks get really long, dozens of steps, needing tons of data from the web or papers. So their key solution, the breakthrough for these long tasks, is what they call the context management paradigm. Context management. Yeah. Okay. Is this tackling that classic context overflow problem where the AI basically forgets what it was doing halfway through because its memory window is full?
Precisely. That's exactly what it's designed to prevent. They use something called Markovian state reconstruction.
Markovian, meaning it relies only on the current state, not the whole past.
Exactly. It's clever because the agent isn't conditioned on the entire ever-growing history. Think about it, you'd waste so many valuable tokens just repeating old stuff.
Okay, that makes sense from an efficiency standpoint.
Yeah.
But how do you compress that history effectively? How do you make sure you don't lose something crucial from way back?
Good question. At any point, the agent is only conditioned on 3 things. 1, the original question is trying to answer. 2, an evolving report. This is really the core of it. It acts like a compressed memory, a running summary. And 3, the immediate context, just the very last action it took and the observation it got back.
This evolving report. That sounds like the secret sauce. It's synthesizing as it goes.
Yeah, it's a structured summary of everything important found so far. That's the key.
I definitely see the engineering need for that. But doesn't relying on a summary instead of the raw history introduce a pretty big risk? I mean, the model creating that summary has to constantly decide what's important, what to keep, what to throw away if it drops a key piece of evidence from 10 steps back.
Oh, absolutely. It introduces risk, no doubt. And that's why the training, which we'll get to in a bit, is so absolutely critical. It has to learn how to summarize effectively for the task. But structurally, this whole context management thing, it enforces structured reasoning. It forces the agent to periodically stop, think, and synthesize its findings into a coherent report. It can't just rely on a long, messy stream of consciousness. It mirrors, in a way, how effective human research works, too. You have to structure your thoughts.
Right. You write outlines, interim summaries. It forces clarity, okay? And to actually do this research, the agent needs tools, right? To interact with the world. What's in its toolkit?
They gave it a solid set of 5 integrated tools. This defines its action space, how it can interact. First, obviously, standard web search, Google in this case.
Standard enough. But the next one you mentioned, the visit tool, that sounds more complex than just clicking a link.
It really is. It's much more advanced. So when the agent decides to visit a URL, it first uses Gina to parse the web content.
Gina, that helps deal with messy website layouts, ads, all that stuff.
Exactly. It cleans it up. And then this is a crucial part. It uses a separate summary model to extract only the specific information the agent needs right then, based on its current goal.
So it's not just scraping the whole page into the context, it's targeted extraction.
Precisely, goal-directed extraction. It pulls the answer to the agent's implicit question, not the whole document.
That must cut down the noise in the context window hugely.
Yeah.
Very efficient.
Massively. Okay, so beyond the web stuff, they included a Python interpreter. That's vital for any kind of calculation, data analysis. Real-world research often needs numbers crunched. Then Google Scholar integration, so it can access academic papers, making it a proper scholarly investigator.
Okay, now it's getting serious.
And finally, a file parser. This lets it analyze local documents, maybe PDFs, even multimedia files potentially, so it's a pretty comprehensive and flexible kit.
Search, visit, Python, Scholar, file parser. Yeah, that covers a lot of ground. Okay, so that's the architecture, the structure, the tools. Now let's get into what sounds like the real innovation here. The training. You said it's not just standard fine-tuning. It's a dual-phase thing built on this Qwen 3 base model. Walk us through that training structure.
Right. This is an end-to-end framework they engineered specifically to instill agency into the model. The first phase is really interesting. Agentic mid-training. They also call it continual pre-training, or CPT.
Mid-training. Why do you need that extra step? Why not just jump straight to fine-tuning it on tasks, teaching it to use the tools?
Because your typical large foundation models, even the really powerful ones, they're mostly trained on, well, just massive amounts of text. They lack what the paper calls agentic inductive bias.
Meaning they don't inherently know how to act like an agent, how to plan, use tools, decompose problems.
Exactly. They don't naturally understand that workflow. Goal plan, observation, or reason next action. CPT is the bridge. It provides that missing prior knowledge. It's like installing the basic operating system for being an agent before you load the specific applications.
Okay, so CPT teaches it the mechanics of being a researcher before it actually tries to solve hard research problems. What kind of data does it learn from in this CPT stage?
It uses synthesized data, and this data is specifically designed to cover the whole agent workflow systematically. Things like how to generate a good research question itself, question synthesis, how to plan the steps, planning action, how to reason about the results of an action, reasoning action, and how to decide what to do next, decision-making action.
So it learns the patterns, the structure of react thinking.
Precisely. It builds that foundational muscle memory for using tools and generating the structured thought process needed.
Got it. And phase 2 is agentic post-training. This uses supervised fine-tuning SFT first, then reinforcement learning RL. And this is where the synthetic data aspect gets really wild, right?
This is, I think, the most revolutionary part of their whole approach. They developed a fully automated, highly scalable way to generate all the training data needed. Think about what that means. They completely remove the need for expensive, slow, often inconsistent human annotation of complex research-level problems.
Okay, hold on. Fully automated synthetic data for research tasks. We always hear concerns about synthetic data quality. How good can it be? They claim it generates superhuman level or PhD level research questions. Is that realistic?
Well, the complexity comes from the structure they generate. They're not just generating random questions. They create these verifiable agent trajectories, the whole reasoning path. And these generated tasks inherently involve things like reasoning across multiple sources, needing multiple hops to find information, dealing with uncertainty, or even conflicting data points.
So the tasks themselves are complex by design.
Exactly. The kind of messy, difficult stuff that defines actual PhD level research. A human annotator. They couldn't create this volume of data, and they definitely couldn't easily verify every single reasoning step in a long chain is correct. The system does.
So they're using AI to generate the really hard homework needed to train a smarter AI.
You got it. And this creates what they call a data flywheel. It's a really powerful concept.
Flywheel, meaning it feeds itself.
Yes. As the agent gets better through training, it becomes capable of generating even more complex, more challenging, higher quality synthesized data for the next round of training. So the model is essentially bootstrapping itself, creating its own increasingly sophisticated curriculum. It iteratively improves.
That's potentially a massive advantage over traditional RL, where getting good training data is often the biggest bottleneck in expense.
Yeah.
Okay, but for that RL phase to actually work, the learning environment needs to be stable, right? You mentioned tool use. The real web is messy. APIs fail, latency varies.
Absolutely critical point. If your agent is trying to learn a policy, and half the time the search tool hangs or returns garbage, the learning signal gets totally corrupted. It's just noise. They solve this using a unified sandbox during the training phase. This sandbox perfectly mimics the behavior of the real tools, but in a controlled way.
So it insulates the training loop from real-world chaos.
Precisely. It ensures that every time the agent calls search or visit or the Python interpreter inside the sandbox, it gets a deterministic, stable, predictable result. This makes the reinforcement learning process much, much more stable and effective.
That makes total sense. A stable environment is crucial for the learning algorithms to actually converge. Okay, so that brings us to the RL dynamics themselves. What were they optimizing for? What did the learning signal look like?
They were very pragmatic here. The algorithm itself was an adaptation of GRPO, but the focus wasn't on some fancy new RL algorithm. It was on stability and using that clean data signal effectively. They used a strict on-policy approach. And the key thing, the reward signal was incredibly simple. Pure 0-1, binary.
0 or 1, meaning?
Meaning, did the agent get the final answer correct? Yes. 1 or no. That's it.
Wow, really? No points for trying, no partial credit for finding some relevant info or using tools correctly?
Nope. They reasoned that the SFT phase before RL already taught the agent the basic mechanics and formatting of tool use. The RL phase was purely about optimizing for the final outcome, getting the right answer. Not about how long it took or how elegant the process was, just correctness.
Interesting, focusing purely on the outcome. And that simple reward led to a really surprising finding in their experiments, didn't it? Something about context window limits.
Yes, this was one of the most counterintuitive, but I think important results they reported. It's in figure 9 of the paper, for those following along. They ran this experiment where they took a model that was deliberately constrained, say it only had a 32,000 token context window, and they trained it on the same challenging curriculum designed for a much more capable model, maybe one with 64,000 tokens.
Okay, so you're giving the smaller model problems that ideally need more context than it actually has to find the best or most thorough solution path.
Exactly. So when this constrained 32K agent tried to follow the long, detailed, optimal path the 64K agent might take, what happened?
It would run out of context overflow.
Right, and because the reward was 0-1 for correctness, running out of context meant failure. 0 reward, consistently. This constant negative feedback, this lack of reward for the thorough but too long path, forced the constrained 32K model to discover something else. They called them more concise, potent action sequences.
So because it literally couldn't afford the long, rambling path, it had to find shorter, smarter shortcuts to the right answer.
Precisely. It couldn't afford the luxury of exploring every single avenue. It was forced, by the constraint and the reward signal, to become extremely efficient and find the most direct route to the solution that fit within its limits.
That's fascinating. It's like efficiency born from frustration. The best path guarantees failure, so it's incentivized to find a fundamentally different, more compact strategy.
It really challenges the idea that bigger context is always better. It suggests that capability isn't just about raw context length, but also about how effectively an agent learns to operate within its given constraints. Resource constraints can actually drive a certain kind of intelligence.
A key lesson there. Okay, so this efficient foundation, the training, it led to good performance on benchmarks.
Yes. Combined with the rigorous training, it allowed Tongyi Deep Research to achieve really strong, stable scores on standard benchmarks like GAI, WebWalker QA, and also on the very complex text-only questions from humanities' last exam. Robust performance.
Now, sometimes even a single efficient agent isn't enough for the truly monstrous problems, right? The really thorny ones. They developed something called heavy mode for those situations, a test time strategy.
Right. Heavy mode is their approach for scaling up the research effort when the agent is actually deployed on a very difficult task. It's about maximizing exploration and the chance of success.
How does heavy mode work?
It's a two-phase process. Phase 1 is the parallel research phase. Here, they don't just run one agent. They deploy an agent's maybe 8, 16, whatever makes sense, all working on the same problem in parallel.
Okay, multiple researchers tackling the same question from different angles.
Exactly. And because each agent is using that efficient context management paradigm we talked about earlier, they can explore diverse paths without immediately hitting context limits. Each one builds its own evolving report.
So now you have, say, 16 agents potentially finding different pieces of information, maybe even conflicting conclusions, all summarized in their individual reports. How do you consolidate that? You can't just jam 16 reports together. You'd overflow again.
And that's the elegance of phase 2, the integrative synthesis phase. They use a separate, dedicated synthesis model just for this aggregation step. But, and this is critical, they don't feed the synthesis model the entire messy step-by-step trajectory from all 16 agents. That would be way too much context.
So what does it get?
It only gets the final compressed reports, those evolving state summaries, sub from each of the parallel agents.
I see. So that compressed memory structure they built for individual agents, it doubles as an efficient way to communicate the essence of each agent's findings to the synthesizer.
You've got it. These reports capture the core logic, the key findings, the final conclusions, without all the noisy intermediate steps. Because these reports are already summaries, the synthesis model can look at the outcomes of many different strategies side by side, all within a manageable context window.
And by comparing these diverse, condensed summaries, it has a much better chance of identifying the truly best, most comprehensive answer.
Exactly. It allows for intelligent aggregation of diverse explorations. That report compression is absolutely key to making this test time scaling feasible.
And did it work? Did heavy mode actually boost performance significantly?
Oh, yes. The results were substantial. For example, on those tough humanities last exam questions, using heavy mode pushed their score up from around 32.9% to 38.3%.
That's a pretty significant jump just from parallelization and smart aggregation at test time.
It really validates the whole system design. The efficient agent architecture makes parallel runs practical, and the structured memory system enables that intelligent final synthesis. So Tongyi Deep Research really does set a new standard, a new state-of-the-art for open-source deep research agents. And importantly, it often matches or even beats strong proprietary systems in some areas while being way more interpretable and keeping that amazing 3.3 billion active parameter efficiency.
Okay, so wrapping this up, what's the big takeaway here for you, the listener? Well, it seems this deep dive shows pretty clearly that the combo of automated synthetic data, this clever dual-phase training, and a really stable RL setup.
Yeah.
It means open source AI isn't just playing catch-up anymore. In this area, autonomous research, it's reaching parity or getting very close to the frontier proprietary models.
Absolutely. And we're seeing this deliberate strategic shift happening across the field. Developers aren't just building specialized tools anymore. They're engineering these general purpose agents. Models like this are learning how to apply reasoning, memory, tool use, autonomy, scalable skills across fundamentally different kinds of tasks.
The era of the truly autonomous, maybe even self-improving unified agent model seems to be arriving. So the final thought to leave you with, what happens next? What new levels of scientific discovery, business innovation, or just sheer productivity get unlocked when these agents, trained perhaps on data they generated themselves, can be reliably deployed across all sorts of fields with less and less human guidance? How soon until the default first step for any complex research task is just delegating it to an agent? That's a profound shift in capability to think about.